Bismillah ar-Rahman ar-Rahim. We have the following optimization problem. The optimization variables are x1, x2 to xn. The variables satisfy the constraint that their sum is equal to 0. Alpha is a given parameter. Alpha is a strictly positive real number. We are interested in minimizing the following objective function, which is the difference of two terms. The first term is the sum of the squares of the x's multiplied by alpha. The second term is a double sum over all possible pairs of the x variables. This double sum is squared and is subtracted from alpha times the sum of the squares. To solve this constraint optimization problem, the first step is to simplify this double sum. Note that reordering the optimization variables does not change the constraint and does not change both terms in the objective function. Hence, without loss of generality, we will assume that the variables are arranged in a descending order. x1 is greater than or equal to x2, which is greater than or equal to x3, and so on. In the double sum, if the two indices are equal, the summand is equal to 0. We can rewrite this double sum as 2, and then we have index I going from 1 to n minus 1. The other index, j, starts from I plus 1. If j is equal to I, this absolute value is equal to 0, and the upper summation limit is n. This factor of 2 takes into account that we have the absolute value of, say, x3 minus x5, and we also have the absolute value of x5 minus x3, which is equal to the absolute value of x3 minus x5. Because of our ordering assumption, we know that xi is greater than or equal to xj. This absolute value can be written as xi minus xj. If the index I is equal to 1, we have n minus 1 terms, 2 times x1 minus x2, 2 times x1 minus x3, all the way to 2 times x1 minus xn. If I is equal to 2, then we have n minus 2 terms. The first one is 2 times x2 minus x3, and the last one is 2 times x2 minus xn. If I is equal to 3, we have n minus 3 terms. The first one is 2 times x3 minus x4, and the last one is 2 times x3 minus xn, and so on. If we rewrite this sum as x1 times some coefficient plus x2 times some coefficient, and so forth, what is the coefficient of xk? What is the coefficient of x1? x1 appears in these n minus 1 brackets, and there is this factor of 2. So x1 is multiplied by 2 times n minus 1. What about x2? x2 appears in these n minus 2 brackets. However, it also appears here. From here, x2 is multiplied by 2 times n minus 2, but then there is an extra minus 2 because of this bracket. So the coefficient that is multiplied by x2 is 2 between brackets n minus 3. What about x3? These are n minus 3 terms, but x3 is also here and is also there. So we have minus 2, minus 2. All in all, the coefficient of x3 is 2 times n minus 5, and so on. The double sum that we have in the objective function can be written as a single sum. Summation k from 1 to n of xk. xk is multiplied by 2 times n plus 1 minus 2k. Our optimization problem is constrained. The sum of the x's is equal to 0. I will convert it into an unconstrained optimization problem using the variables from x1 to xn minus 1. The constraint means that xn is equal to minus x1 minus x2 all the way to minus xn minus 1. So this is minus summation k from 1 to n minus 1 xk. Rather than solving a constrained optimization problem, we can just reduce the number of variables by 1, and whenever we see xn, we replace it by this quantity here. If we go back to this summation, we can first separate this into n plus 1 times the summation minus 4, and then the summation k from 1 to n k xk. This term goes away because the summation is equal to 0. Then we can exploit this fact by isolating the nth term. This can be written as minus 4 summation k from 1 to n minus 1 k xk. The nth term is minus 4 n x of n, which can be written as above here as minus summation k from 1 to n minus 1 xk. This double sum now is written in terms of the optimization variables from x1 to xn minus 1. When we combine these two sums, we get that the double sum is summation k from 1 to n minus 1 xk multiplied by 4n minus 4k. We can think of this summation as an inner product of two vectors. Vector y contains the optimization variables from x1 to xn minus 1. Vector b is a vector with n minus 1 components, and its first element is 4 times n minus 1, its second element is 4 times n minus 2, and so on. The dot product of these two vectors, which can be written as y transpose b or b transpose y, is this summation here, which is the double sum that appears in the objective function. Thus, this term here can be written as y transpose b squared or y transpose b times b transpose y, like this. The first term is the sum of the squares. We can isolate the nth term as alpha xn squared. We know that xn from the constraint is minus the sum of the other x values. This can be written as minus the inner product of the all one vector in n minus 1 dimensions and vector y, which contains the optimization variables from x1 to xn minus 1. So defining vector d as a column vector with n minus 1 ones, and this is vector y. This summation can be written as d transpose y or y transpose d. So xn squared is equal to y transpose d squared, which can be written as y transpose d times d transpose y. In other words, this term in the objective function can be written as alpha y transpose d d transpose y. What about the first term? This is the L to norm squared of vector y, which is y transpose y. This term is alpha y transpose y. Alpha times xn squared is alpha y transpose d d transpose y. Finally, we subtract the square of the double sum. This is y transpose b, b transpose y. We can take y transpose as a common factor on the left, y as a common factor on the right. The objective function is just a quadratic form. It is a column vector transpose times a square matrix of size n minus 1 by n minus 1, and then the vector itself, vector y. If we define vector A to be equal to the square root of alpha, which is a positive real number, times the all one vector d, then the matrix of the quadratic form is alpha times identity plus A transpose minus B transpose. We need now to find vector y that minimizes the objective j. This is now an unconstrained optimization problem. Once we obtain vector y, we know the variables from x1 to xn minus 1. The last variable, xn, can be obtained using the constraint that the x's sum to 0. Let's now review quickly the theory of minimizing quadratic forms. If we are minimizing y transpose phi times y, and phi is a symmetric matrix, then we know that the eigenvalues of phi, because it is symmetric, are all real valued. If lambda q is an eigenpair of phi such that lambda is negative, then y transpose phi y is unbounded below. It can be made as small as we wish. We can push it towards minus infinity. The reason for this is that we can choose y to be eta, which is a positive real number, times the eigenvector associated with the negative eigenvalue lambda, q. So y is eta q. In this case, the objective function y transpose phi y is equal to eta squared. Then we have q transpose phi q. But q is the eigenvector of phi associated with the eigenvalue lambda. Phi q is equal to lambda q. The quadratic form now can be written as lambda times eta squared times q transpose q. This is the L to norm squared of vector q. Vector q is an eigenvector, so it is non-zero. This L to norm squared is strictly positive. Eta is a positive parameter. Lambda is less than 0. By choosing eta to be large enough, we can make this quadratic form approach minus infinity. The quadratic form is unbounded below. If all the eigenvalues of phi are non-negative, we have the inequality that y transpose phi y is greater than or equal to lambda min of phi times y transpose y. Now lambda min is greater than or equal to 0. In this case, this will be a lower bound on the quadratic form. We can make this lower bound equal to 0 if y is equal to the all 0 vector. If we go back to our problem, since we have discovered that the objective function is given by this quadratic form involving this symmetric matrix, then we have two cases. If the symmetric matrix has one strictly negative eigenvalue, then the objective function is unbounded below. If all the eigenvalues are non-negative, which means that this matrix is positive semi-definite or positive definite, in this case, the minimum of the objective function is 0, and one way of achieving it is by setting y to the all 0 vector, which means that all the optimization variables are equal to 0. To finish this problem off, we need to investigate the eigenvalues of the matrix of the quadratic form, which is alpha times identity of size n minus 1 by n minus 1 plus A transpose minus B transpose. Because we have this alpha times identity, we know that the eigenvalues of the matrix here are simply the eigenvalues of A transpose minus B transpose plus this alpha. Our concern now is to obtain the eigenvalues of A transpose minus B transpose, which can be written in this way. I have a matrix of size n minus 1 by 2. Its first column is A and its second column is B. Then we have a square matrix of size 2 by 2. We have 1, minus 1, 0, and 0. And then we have the transpose of this matrix. That's a matrix of size 2 by n minus 1. Its first row is A transpose and its second row is B transpose. What is the rank of this matrix? At most 2. This n minus 1 by n minus 1 matrix has at most 2 non-zero eigenvalues. Now let's exploit a result from matrix analysis. If we have two matrices phi and omega, phi is of size big N by big M and omega is of size big M by big N. Phi omega, which is an N by N matrix, and omega phi, which is an M by M matrix, have the same non-zero eigenvalues. Thus, to obtain the two potentially non-zero eigenvalues of this n minus 1 by n minus 1 matrix, we can just move this matrix to this side here. And rather than working with an n minus 1 by n minus 1 matrix, we can work with a 2 by 2 matrix. When we do this and expand, we get the following 2 by 2 matrix: A transpose A transpose B, minus A transpose B, and minus B transpose B. We can obtain the eigenvalues using the standard procedure to obtain this quadratic equation, which has two solutions. Those two solutions are the potentially non-zero eigenvalues of A transpose minus B transpose. Those eigenvalues are denoted by lambda plus and lambda minus. Note that these two eigenvalues can be explicitly written down in terms of the two parameters in our optimization problem: the integer n, which is greater than or equal to 2, and the positive real number alpha. The eigenvalues depend on three quantities: A transpose A, B transpose B, and A transpose B. A is equal to the square root of alpha times the all one vector. A transpose A is alpha times the inner product of the all one vector with itself. A transpose A is equal to alpha times n minus 1. Vector B is a vector with the components 4 times n minus 1, 4 times n minus 2, all the way to 4 times 2 and 4 times 1. B transpose B is the sum of the squares of the elements in this vector. B transpose B is equal to 16, and then the sum 1 squared plus 2 squared, all the way to n minus 1 squared. We use the result that summation I from 1 to m of I squared is 1 over 6 times m plus 1 times 2m plus 1. We multiply by 16 and we replace m by n minus 1 to obtain this for B transpose B. Finally, we need the inner product of vectors A and B. This will have the factor 4 and the square root of alpha times the sum of the positive integers from 1 to n minus 1. Here we use the result that summation I from 1 to m of I is equal to 1/2 m plus 1. We use this here after replacing m by n minus 1. So far, we have converted our constrained optimization problem in n variables into an unconstrained problem in n minus 1 variables. Those are the components of vector y. Our objective function is a quadratic form involving a symmetric matrix. If this matrix has an eigenvalue that is strictly negative, then the objective function is unbounded below. If the eigenvalues of this symmetric matrix are all non-negative, that is, if the matrix is positive definite or positive semi-definite, then the minimum of the objective function is equal to 0. This symmetric matrix has n minus 3 eigenvalues that are equal to alpha, which is a given positive real number. The other two eigenvalues are alpha plus lambda plus and alpha plus lambda minus. Is lambda plus positive? Lambda plus is this square root and the plus sign. This is 1/2. Under the square root, we have the square of A transpose A minus B transpose B. Let me write this as plus 4. Between brackets, we have A transpose A, B transpose B, minus the square of A transpose B. Then we have plus 1 over 2, A transpose A minus B transpose B. By Cauchy-Schwarz inequality, this term here is greater than or equal to 0. Because the Cauchy-Schwarz inequality tells us that the magnitude of A transpose B is less than or equal to the square root of A transpose A times the square root of B transpose B. In other words, this square root here is greater than or equal to the absolute value of A transpose A minus B transpose B, which we have here, without absolute value. This means that lambda plus is guaranteed to be non-negative. Now we can characterize the solution to our optimization problem in a more precise way. We need to focus on this eigenvalue. Our objective function is unbounded below if this eigenvalue is negative. Lambda minus is equal to minus 1/2 times this square root plus 1/2 A transpose A minus B transpose B. We can move this term to the other side and multiply both sides of the inequality by 2 to get this inequality here. Can we square both sides of this inequality in order to simplify it? Well, the left-hand side can be negative. Alpha is strictly positive, but it may happen that for a particular choice of the values of alpha and n, that B transpose B is greater than 2 alpha plus A transpose A. Can the left-hand side be negative and greater in absolute value than the right-hand side? If the left-hand side is negative, then the absolute value is equal to minus 2 alpha plus B transpose B minus A transpose A. Because alpha is strictly positive, then this is less than or equal to B transpose B minus A transpose A. This is equal to the positive square root of A transpose A minus B transpose B squared, which is less than or equal to the square root of A transpose A minus B transpose B squared, plus the non-negative quantity, which is 4, and then between brackets, we have A transpose A, B transpose B minus A transpose B squared. And we know that this is non-negative by the Cauchy-Schwarz inequality. Yes, the left-hand side can be negative, but in absolute value, it cannot exceed the right-hand side. We can square both sides. The right-hand side will give us A transpose A squared plus B transpose B squared. And then if we look here, this will give us minus 2 times the product, but then there's plus 4 here. So we'll have 2 A transpose A, B transpose B, and then we have minus 4, the inner product squared. On the left-hand side, we have 4 alpha squared. We have the square of this bracket here. So these are 3 terms, A transpose A squared, B transpose B squared, minus 2 A transpose A, B transpose B. And then we have the cross term, which is 2 times 2 alpha times this guy. On both sides, we have A transpose A squared. And also on both sides, we have B transpose B squared. These terms go away. And then this term here can be joined to the left-hand side as minus 4 A transpose A times B transpose B. Also, this term can be moved to the left-hand side as 4 A transpose B squared. Now we can use our previous results to write down everything in terms of the positive real number alpha and the integer n. We have 4 alpha squared from here. We have here 4 alpha squared times n minus 1. Together, these two terms give us 4n alpha squared. And from the remaining terms, we can also get 4n alpha as a common factor. We can divide both sides by 4n. And from this bracket, we can extract n minus 1 as a common factor. After simplifying, we get this other term as minus 4 over 3 n minus 1 alpha. And then from here, we have n plus 1. Because alpha is strictly positive, we can divide by alpha and then move this part to the other side to obtain this inequality alpha less than 4 over 3 n times n minus 1 times n plus 1. If this inequality is true, then we have one eigenvalue that is strictly negative. The objective function is unbounded below. But if alpha is greater than or equal to 4 over 3 n cubed minus n, note that we can write this as n squared minus 1, and then we multiply by n to get n cubed minus n. If alpha is greater than or equal to this quantity, then the minimum is equal to 0. The minimum is achievable by setting vector y equal to the all 0 vector. This is equivalent to choosing the optimization variables from x1 to xn minus 1 as zeros. Consequently, the optimization variable xn will also be 0, given the constraint that the sum of the x's must be 0. So we can achieve this 0 by choosing all the variables to be equal to 0. If alpha is equal to this quantity here, then our symmetric matrix is positive semi-definite with an eigenvalue that is exactly equal to 0. In this case, the minimum is still 0, but we can achieve the minimum in infinitely many ways. Choosing xk to be equal to n plus 1 minus 2k, where k is an integer from 1 to n, is one of these ways.